Swayam Prabha. Digital India. Educated India.
So, good morning. Okay. So, I hope you are able to see these, just go through your notes with respect to construction of a carry-lookup adder that we saw in last class, and now you are in a position to appreciate how carry-lookup adder can do addition of two n-bit numbers in log n time, while a carry-ripple adder will take n units of time, right. And we stopped with what is the total area required, is it order n or order n log n. So, did somebody look into it? I said the size is still order n. Is this a correct statement or a wrong statement? Please note that the 0th stage or A0, right, is useless after, does not do any computing at all. This, so this stops here, there is no need for computing it beyond this point. For the first stage there is no need for computing beyond this. So, these two are empty in the after this first stage or second stage, whatever you call, and in the these three are empty here and 4 are empty, right. So, please note that if you go back to the previous slide, in the 0th stage only 0 points to 0 and 1 has reached this. The moment you start pointing to this, then after that you do not need this, correct, right. At the end of first stage, this is already two entries are pointing to this. So, if I take the nth element, so how do you analyze this size? If I take the nth element or if I take the kth element, when will it reach this? So, every time it is going to point to some entry which is twice as far as what it was pointing earlier. For example, this was pointing 1 before it, in the next stage it will point to 2 before it, the next stage it will point to 4 before it, and it actually becomes useless for computing, meaning there is no constructive computing necessary after it starts pointing to the last element, correct. So, every time I double the distance to which I point to, and if I point to the last element, then after that there is no computation left for me. So, how much time will I take to point to the last element, or how many steps will I take to point to the last element? Log of, if I am the kth element, how many steps will I require to go and reach the first element? Every time I am reaching double the distance, double the distance. So, first I am pointing to 1 before me, next 2, next 4, next 8, like that. How much time will I take to reach k? Log k, right. So, I need log k computation. So, I need to be repeated for log k times, right. After that it is just that value can keep propagating. So, the circuit actually, I need a circuit for computation of that star operator, correct. That circuit needs to be replicated log k times for the kth element. So, how many such replications I need? Can I now write it as a formula? So, for the kth element I need log k replications, at least in log k steps I need that circuit to repeat, right. So, what is the total number of repetitions? Note that this is the same star operation. So, what is the total number of repetitions? Sigma k equal to 1 to n log k, some seal we can put. So, this can be approximated to can we do this? Sum is right. So, this should be certainly less than or equal to this, because we are only interested in discrete points while this is a continuous function, okay. So, how do you integrate log x dx? X log x minus x. X log x? X log x. and this will go from 1 to n. Okay. So this will be order n log n minus n. Okay, so that is fine. Or n into log n minus 1, this will be still order n log n. Okay, so this is wrong. Okay, fair enough. Are you able to follow this? Okay, good. So I want you to find. See, I have voluntarily introduced errors in my slides. Okay, I want you to find out where the errors are. Okay, and I may ask you a quiz question on. See, I don't take attendance, but the way I ensure attendance is that I'll ask one quiz question on, what are the errors in my slide. Okay, right. Okay, now we will go into the next important operations in computing, namely multiplication. Okay, now how do we multiply? So let us go here. Suppose I want to multiply 95 into 4, 95 into 14. Okay, so I just say 4 plus 4 into 5, 20, 4 into 9, 36, 380, correct, and then 95, then I sum it. Fine, is it okay, right? So each one of this is a partial product. Then you actually sum up the sum of all partial products. So high school multiplication involves two steps. One is generation of partial products, and two, summing up the partial products. Fine? Are you able to understand this? Now, entire multiplication should concentrate on how effectively we can do this, or how quickly we can do this, right? So there are several algorithms that are reported. Let us not bother so much, but we'll introduce the latest algorithm. So what we will be teaching in this class is called a Wallace tree multiplier. Okay, fine. Okay. So please understand that I need to generate partial products and I need to sum up these partial products. And please note that this is not decimal arithmetic, we are going to handle it in binary. Okay. So let us say I want to multiply right. So what are the partial products here? I take this 0 and AND it with 1101. So 0 0 0 0 1 1 0 1 0 0 0 0 1 1 0. Okay, correct, and we add this. So the generation of the partial product is basically to take every bit of one of the so every bit of the multiplier. Let me call this as multiplicand. Let me call this as multiplier. Okay. So we take every bit of a multiplier and multiply with the every bit of the multiplier and multiply with the multiplicand, or AND it with the multiplicand. So we do what we call as a every bit of the multiplicand get AND with one of the bits of the multiplier. Next this, next this, next this. Okay. So this is how. So these are all the partial products that we see here. Let me call it PP1, PP2, PP3 and PP4. So if the multiplicand is n bits and your multiplier is m bits, we get m partial products, correct? We get m partial products and with shifts, right? It will keep shifting, right? So the last one would be shifted by m bits. So it will be, this will be n plus m bits, because this is n bits plus n plus m minus 1 bits, n plus m minus 2 bits and so on, right? So this is effectively, these are all zeros, as you see, okay? We can still fill up, okay? So I could say that we have now m numbers each of n plus m minus 1, which also to make this whole thing look easy, right? But these are all always zeros, these are all always zeros. When we actually construct a circuit, please note that we will not try to have some elements for these, right, some circuit elements for these, because they are already zero. So this is the answer itself. First bit of your answer is generated the moment you generate the partial product, and so on. Is fine? Are you able to follow this? Okay. Now, any doubts in this? Right. So I generate partial products and I sum them. The way I generate partial product in binary arithmetic is to take a bit and AND it with the bits of the other operand, and keep doing it for every bit of the multiplier, and then sum it up with necessary left shifts. Fine? Able to follow? Okay. Now suppose, let us say, so in partial product I get n or m partial products and I am adding those m numbers. So how can we add two numbers? See, so for example, suppose I say, so how can I add three numbers? Let us go and do this. See, suppose I want to add 1101 with 1010 with 1110. Okay, suppose I want this, right? For each of, so these are three numbers A, B and C, okay. The way I can add it is, take each of this in parallel. The quickest way of adding it is, let us take this in parallel, each of these columns in parallel, right. Let me use a full adder circuit with 3 inputs. It will generate me a sum bit and a carry bit. So this will generate me a sum bit as 1 and a carry bit as 0. I am writing the carry bit here, okay. This will generate me a sum bit of 0 and a carry bit of 1. This will generate me a sum bit of 0 and a carry bit of 1. And this will generate me a sum bit of 1 and a carry bit of 1. Right. Now you add these two, this will be 1, 0, 1, correct? Fine, right? So what is this? This is 13, 10 and 14. So this is 27, 37. So this is 32 plus 5, 37, both are equal. Okay. So what did I do? I converted the problem of adding 3 numbers to the problem of adding 2 numbers, because I have an adder which can add only 2 numbers. Now what I have done, I have converted the problem of adding 3 numbers to the problem of adding 2 numbers. And how much time does it require for me? 1 unit of time, because I use a full adder circuit for this. Correct? I use a full adder circuit for this. So I use 4 full adders in parallel concurrently and immediately generate two numbers from 3 numbers. And those 2 numbers I can use the carry lookout adder and add it. Right? So assuming that the carry lookout adder will take log n time, so adding 3 numbers can also be achieved in log n plus 1 time. That 1 is the full adder delay. Is it okay? Right? So this type of an addition is called as carry save addition. Right? So every time what I did, I took each of these columns in parallel, generated a sum bit and a carry bit, and I just arranged the carry bit with one shift to the left and added the sum bits to that. Right? So I saved the carry bit for adding at a later stage. In this stage I get the sum bit and also a carry bit which I save, and I use it at a later stage for finding the result. Right? So this is what we term as carry save addition. Right? Any doubts in this? So the problem of adding 3 numbers get translated to the problem of adding 2 numbers by this carry save addition, and this we will be using for our multiplier. Right? Now how can we do this here? So I actually have 4 numbers to be added. I can take the first PP1, PP2 and PP3, right, and I can generate what? I will generate 2 numbers, say let me say PP1 dash and PP2 dash. This PP1 dash and PP2 dash I will take and add it with PP4 to generate another 2 numbers, namely PP1 double dash and PP2 double dash, and these 2 I can use a carry lookout adder. Okay. So the problem of adding 4 numbers, right, I can just in constant time I can convert these 3 numbers into 2 numbers, again in constant time this will take order 1 time, 1 full adder, and again in constant time I can convert these new, there are two new numbers that are generated along with the old PP4, that I can convert into 2 times. So in log n plus 2 steps, log n for this addition, this is again I can use a carry lookout adder, plus 2 steps I can finish off multiplication of these 2 numbers. Not log n plus 2, in this case this is 4. So because we have n is 4, right. Now this is the basis, and now we will extend it for, I have just shown it for multiplying 2 4x4 two 4-bit numbers. Now I will extend it for multiplying 2 n-bit numbers, right, and this is the basis of Wallace tree multiplication. Fair enough? Are you able to follow? Did you all understand what is carry save addition? Palakkad? Okay. And how the carry save addition could be used in the context of multiplication, right? I just gave this example here. These 2 are the things that I want you to understand here. Fine? Okay, now we will go back to, I will formally tell you how carry save addition works, right. So given 3 n-bit numbers x, y and z, the circuit computes a n-bit number u and a n plus 1 bit number v such that x plus y plus z equal to u plus v, and that is what we had seen here. So let us see how that's, so this is x, so this is x which is an n-bit number, 8-bit number, and this is y which is also another 8-bit number, this is z which is also another 8-bit number. Now I have generated another 8-bit number which is u. This is very important for you to note, this u is 8 bits and the v is actually 9 bits. Please note that this 0 is just appended. I shift the carry by 1 bit to the left, as we had seen in the carry save addition. So, formally stating, if I want to add 3 n-bit numbers, that problem could be converted in constant time to a problem of adding one n-bit and another n plus 1 bit number, correct. Adding 3 n-bit numbers in constant time can be converted to a problem of adding one n-bit and one n plus 1 bit numbers. Please note that n and n plus 1 are very important to note here, because finally this is what we will use to construct the final circuit. Okay, is this fine? Any doubts? 2 n-bit numbers, 3 n-bit numbers become addition of 3 n-bit numbers become addition of 1 n-bit and 1 n plus 1 bit number in constant time using n full ladders. Okay, is this clear? Yes or no? Yes. Okay. So this is the basic circuit. As you see here, you will have n full adders, and each full adder will generate a sum bit which we call it as U0, U1, U2, U3, U4, U5, U6, U7, and each full adder will also generate a carry bit which we call, which is V0, which is appended 0. V1 will be generated by this, V2, V3, V4, V5, V6 and V7 and V8. Okay. So U is a n bit number and V is a n plus 1 bit number. Yes.
Is the input of the full adder like restrained to only 3 or like 3 pin full adder or?
Full adder means it's a 3 bit full adder.
Oh,
Okay. It's just a module, right? Yeah. Just as an XOR circuit and a 3 AND gate on OR gate. It will generate sum of 3 bits and the carry of these 3 bits. Right. Fair enough? So this is a construction. So please, I am showing this slide to show that this entire operation will take constant time or order 1 time. 1 is constant. Okay. So we will very quickly go into the multiplier. So this is simple grade school multiplication method. As I explained, we first generate partial products and then in parallel. Please note that this is done in parallel, and then we do carry save addition, which will give us this faster array multiplier. What we call this faster array multiplier was due to Wallace, and so we call it as the Wallace tree multiplier. Wallace is the name of the scientist, but why tree we will just see very quickly why it's. Okay, this is the same thing that I worked out, 1110 with 1101. This is what we need to add. And please note that we have generated 4 partial products, M0, M1, M2, M3. We add these 4 partial products to give me the final answer, which is. So how can we go and do this? So first what we will do is that we will first add, so I have M0, M1, M2, M3. We can do it as follows, right? We just add M0, M1. So this is a very naive way of doing it. We first add M0, M1 and 0, right? We get U1 and V1. Okay. So we add, please note that this is a dummy variable, this is a dummy entry, and these two are partial products, each of 4 and 5 bits, right? So I add 3 numbers, one of 4 bit, another of 4 bit and another of 5 bit, and I get 2 numbers. One is actually a 4 bit number, another is actually again a 5 bit number. Please note that if each are 5 bits, I get 5 and 6, but since both are, 2 of them are 4 and another is a 5 bit, you get an answer which is a 4 bit and a 5 bit number. Now to this 4 bit and 5 bit I add another number M2 which is actually 6 bits, right. So I get a 6 bit number and another 6 bit number, again 4, 5, 6 I get 6 bit numbers, to which I add another number which is 7 bits. So I get 2 7 bit numbers, which basically leads to 8. So this is a sequential way of doing this addition, right. So why I put this slide here is to basically explain you how things can work here. So I have 4 partial products to basically start with. I have 4 partial products and I want to add. This method gives you a sequential way of adding it. So I start with a dummy 0, m0, m1, so 3 numbers that gets converted into 2 numbers, right. But what I want you to note here is, the most important thing that I want you to note here is that this 4, 4 and 5 gives me 4 and 5, okay. 4, 4 and 5 will give me only 2 numbers which are 4 and 5 bits length. As I told you, if I have 3 n bit numbers, it will give me an n bit and an n plus 1 bit number. But if I have say n minus 1, n minus 1 and n, this will give me only n minus 1 and n bit, right, or in sense n, n and n, okay, this is fine. Okay. Now I get a 4 bit number and a 5 bit number and a 6 bit number. This is going to give me 2 6 bit numbers. So if I have n minus 1, n and n plus 1, okay, I get n plus 1 comma n plus 1. Yes, okay. So very simple, if I have 4 bit number, what is the maximum value I have? 15, another would be 15, right, and so this would be 1 1 1 1 1 1 1 1, and if I have a 5 bit here, right, whatever be that 5 bit, let us even take that.
U1 is 5 bit number.
No, here 4 4 and 5 first.
In the second set, isn't U1 5 bit number?
Yeah, so n is 5.
It's not 4 5 6, 5 5 6, right?
No, this is no, but this is 0, right? This is 0. Yeah, but in sense it is 4. See, when we are doing this addition, we are seeing a 4 bit number here. That's what I am saying. So if I have, so let us just prove this formula, right. So if I have n and n plus 1, right, n minus 1, n minus 1 and n plus 1, n. So n is 5 here, okay. So I put even 1 1, okay. So what I will get here, 1 1 1 1 0, the sum bit, sorry, 1 1 1 and 1, sorry. Okay, so this gives me a carry and this gives me 0, okay. So what I will get here, I will get 1 right, okay. So if I have n minus 1, n minus 1 n, I get 6, yeah, n minus 1, n minus 1 n, wait, n minus 1, n minus 1 n, no, I am not doing the addition, right, n minus 1, n minus 1 n, this is n and n, okay. So if I have n minus 1, n minus 1 and n, the worst I will get is n and n, because it is always 0 for me, okay. So this should be fine. So if I have n minus 1, n minus 1 n, I get n and n, is it fine? Nova, what should I get? what will I get?
The sum bit should be 5, right? Because you have 0, 1, 1, 1.
Yeah, 5. That's what I am saying. N is 5 here, no? Sum is 5 and carry is also 5.
Carry bit should be x plus 1.
Why? Carry bit need not be 6 because the carry will be 0 for sure. This carry will always be 0. See, I have put 15, 15 and 31. The maximum I have added. Even for that the carry will always be 0. Can you work it out again? My n is 5. I now say I am adding n minus 1, n minus 1 and n. Okay. So, the first number is 4 bits, second number is 4 bits, third number is 5 bits. This is the maximum I can give. Okay. Even for this maximum value, the sum is going to be 1, 1, 1, 1, 1 and the carry is going to be 1, 1, 1, 1, 0. Because these two are 0, the carry is going to be 0 irrespective of this. So, this is just n bits and this will also be n bits, where n is 5. So, this is 5 bits and this is also 5 bits. So, if I am adding n minus 1, n minus 1, n, I get n comma n. Suppose I do n minus 1, n and n plus 1. Please note that I will get n plus 1 and n plus 1. If I am adding n minus 1, n and n plus 1, yeah, I have done it here. Okay. Now that we can prove that, I will just spend few minutes to prove that. Okay. Suppose I am adding, so let n be 5. So I am adding a 4-bit number with a 5-bit number and a 6-bit number. Right? No, we will come this. Is there any doubt or query about this part? So is there any doubt about this part? No, right? Is there any doubt about what I have marked on red? Is there any doubt? No? Okay. Now we will go to this, the second, n equal to 5. Okay. When n equal to 5, I am doing the second part. I am adding an n minus 1, that is a 4-bit number with a 5-bit number and a 6-bit number. Okay. Now what will be the sum bits here? This will be 1, 1, 1, 1, 0, 1. Okay. And the carry bits will be 1, 1, 1, 1, 1, 0. Okay. So this will be a 6-bit number and this will also be a 6-bit number. Always this carry will be 0. Okay. So when I add an n minus 1 and an n plus 1, I get 2n plus 1. When I add just an n, then I get n comma n plus 1. Okay. So it's fine. If I add an n and n, I get an n comma n plus 1 bit number. So kindly please remember this, right. So simple proof for it is, in this case, for example, let me try and prove this. This is an n minus 1 bit number, this is an n bit number and this is an n plus 1. Please note that since it is n minus 1 bit, let us take the last 3 stages, right. N plus 1, n and n minus 1, the last 3 stages. So here this number would be 0 and this will also be 0, the next this will be 0. Okay. So then I will have some bits here. So let me say these bits are ABC. Okay. So this can at most create one carry, right. So this can create one carry of 1, and if this fellow is also 1, A is also 1, right, irrespective of whether A is 1 or 0, no carry will be generated after this, because the maximum I can have is right. So this can basically create me, so that is what is happening here. so whatever this creates will be a some bit here, okay, and whatever this creates as a carry is going to be 1. So since these two are zeros, right, this particular stage will never generate a carry, because 2 of the 3 bits are zeros, so I cannot generate a carry. So the carry will this always will be 0. You are getting this, right? So that's a simple argument of how an n minus 1, n and n plus 1 can generate will generate only 2 n plus 1 bit numbers. Okay. So these 3 equations are very important because we use this to actually reduce the size of the entire circuit. Okay. So kindly remember this, so that in the next class one of you please tell me, so I will write it down. This is the construction. I will go and talk about this construction in great detail in the next class, but just to give you a heads on. So I am trying to multiply 2 8-bit numbers, right. So I will basically get M1, M2, sorry, M0, M1, M2, M3 till M7, okay, right. So M0, right, these are all the partial products. I will get 8 partial products, M0, M1, M2 till M7, that I will get it in constant time, right, using just I have to AND each bit with the of the multiplicand with the multiplier, or of the multiplier with the multiplicand, okay. So what is M0? M0 is an 8-bit number, M1 is a 9-bit number with 1 0, M2 is a 10-bit number with 2 zeros at the last, M3 is a 11-bit number with 3 zeros. So Mk is the 8 plus k bit number with k zeros at the right hand side, rightmost k bits are zeros, right. Now I have 8 numbers, how can I add it? So I will take M0, M1 and M2, right. M0 is an 8-bit number, M1 is a 9-bit number, M2 is a 10-bit number. So if I add 8, 9 and 10 bits, I will get 2 10 bits. If I have n minus 1 and n plus 1, I will get 2 n plus 1 bits, here n is 9, okay. So I get 2 10 bits because I am adding an n minus 1, n and n plus 1, or k minus 1, k and k plus 1. If I add 3 numbers, I will get 2 k plus 1 bit numbers, so I get 10 10. Now I am adding M3, M4 and M5. M3 is a 11-bit number, M4 is a 12-bit number and M5 is a 13-bit number, okay. When I add again 11, 12 and 13, I get 2 13-bit numbers, okay, I get 2 13-bit numbers. So what I have done is, I had say totally 8 numbers to add here, right. I have now made it as what, 5 numbers. I took the first 3 numbers and made it 2, I took the second 3 numbers and made it into 2, and then there are 2 more left. So now I have made it as what, 1 2 3 4 5 6, sorry, 6. So 8 numbers I actually made it into 6. And how much time I required to convert this 8 numbers into 6 numbers? How much time did I take? Constant time, because carry save adder takes constant time, right. Now this 6 numbers, now I will take these 3 numbers 10, 10 and 13, okay. So 10 could be, again 10 can be treated as the same, k minus 1, k plus 1, right.
10, 10, 13, carry, 11 and 13 will be?
No, 10, 10, 13 I can add, considering each one is as a 10-bit number, another is as 11, I can append some zeros there.
You will be getting 11 and 13-bit numbers, one 11-bit and another.
No, for the time being we will not complicate it, because I have to go and talk about optimization later. So when I add 10, 10 and 13, I will get 2 13-bit numbers, okay. The 10-bit number could be treated as a 11-bit number, this 10-bit as a 12-bit number, and this 13 as 13-bit number. So I can still map this 10, 10, 13 to k minus 1, k and k plus 1. So I will get two 13-bit numbers. Now I have at 13, 14 and 15, again k minus 1, k and k plus 1. So I will get two 15-bit numbers. So this 6 actually became 4 in constant time. Okay. Now this 13, 13 and 15 will give me two 15-bit numbers, and I have another 15-bit number. So these three 15-bit numbers I can add to get, so this 13, 13, 15 I can add, I will get 2. So this 4 became 3 here, and this 3 with this 3 it actually became 2 here. And if I have two numbers I can add it to get this kind. Okay. So lot of redundant hardware is inside this circuit, but one of the thing I need to prove to you is that when I multiply two 8-bit numbers I will get a 16-bit number as an answer, right. If I did not do, if I just say that it is 8, 9 and 10, I say this is 10-bit and 11-bit, right, in our thing, right. If I add three n-bit numbers then I get an n and n plus 1 bits. So if I just go and say this 8, 9, 10, I can consider them as 10-bit numbers, right. And I say if I add three 10-bit numbers then I can say that this will get 10 and 11 bits, while this will get 13 and 14 bits, and if you start expanding this answer will not be 16 bits, it will be much larger, right. You will see zeros only, but when I just delineate this, when I just expand this, it will become a 19-bit or a 20-bit. It will not become 19 or 20-bit. That is why I spent some time to explain you the previous slide, where this, if everything is not n, then I will get only n or n plus 1, n plus 1. So this is what we basically saw in the previous thing. So from that, if you see that 8, 9, 10 will give me 10, 10, 11, 12, 13 will give me 13, 13, 14, 15 is there. Now this 10, 10, 13 will give me 13, 13, this will give me 15, 15, and then I add this and I get this. Okay. So finally I get a 16-bit number as an answer, right. Now what we will do in the next class is two things we need to do. What is the time complexity? So now you see it is a tree, right, it is almost a tree. That is why we call it as a Wallace tree multiplier. Okay. Now we see this is a tree. Now what is the height of this tree? The height of this tree is the depth of the circuit, right. So we will now go and prove what is the height of this tree, and also we will put some effort to see how I can go and reduce the redundancy here. So a lot of zeros get added repeatedly. In this 11, 12 and 13 there are at least 3 zeros that get added here. So now how do we adjust those zeros? So how can I construct a much more optimized circuit than this, right. We will see that. This I have put here to explain you the concept. Most importantly to tell that when I add multiply two 8-bit numbers I will get a 16-bit. If I multiply two n-bit numbers I will get a 2n-bit, or if I multiply a m-bit number with an n-bit number I will get m plus n bits as an answer. Okay. Fair enough. So we will continue this in the next class.